In this video, we're going to be discussing vector addition. Okay, and don't forget to remember that vectors have both a size, or a magnitude, and a direction. So, when you're doing vectors, you cannot simply add them in the normal fashion because of the fact that they have a direction. If you have two vectors, A and vector B, both directed to the right, that is the same as writing this vector A followed by tip to tail vector B. So we can rewrite these two separate vectors as one resultant vector, which means that, in short, A plus B vector gives us C vector. And the same can be true if they were pointed in opposite directions. So, for example, if we had A directed to the right again, and we have B directed to the left this time. Well, that's the same as A to the right, and then remember, tip to tail, B back again. And in this situation, I'm assuming that B is larger than A. In this case, our resultant vector is this space right here. That is C, and it is directed to the left. So in this situation, A, and you'd still add, it's still vector addition, but B is in the negative direction, so it's negative B gives us C. Right? Let's apply some numbers to this. Let's say that our A vector is equal to 5 meters, and our B vector is equal to 6 meters. Well, what does that mean? It means that in our first situation, we had A and B are both directed to the right. So now we're going to go ahead and go A vector plus B vector equals C vector, which in this case is 5 plus 6 equals 11 meters. And if we were to draw that out, it would look something like this. A C resultant vector of 11 meters. But now if we take the same magnitude of vectors, which means the vectors are the same size, but now they're in opposing directions, A and B. Well, now we have to go A vector plus negative B vector equals our C vector. Same as before, we replace in our numbers, we get 5 plus negative 6, and that ends up equaling negative 1 meter, which has meaning. That negative sign right there has meaning. It tells us that our vector is 1 meter in the negative direction, which we determined is to the left. So when vectors are in line, you decide which direction is positive and negative, and then add the vectors accordingly. Where things get a little bit tricky is when the vectors do not line up in the same axis. Both aren't pointing in the x direction or in the y direction. For example, you could have a vector b up of magnitude 3 meters and vector a directed to the right with a magnitude of 4 meters. Well, when this happens, the best way to visualize it until you really get used to it is to walk it out. What's actually happening? Well, what's actually happening is you're starting at this position. You're walking this way 4 meters, and then you are walking up 3 meters. So we're walking it out. Walk it out. And what we're asking when we say what is the resultant vector, what's the total vector, we're asking how far are we from where we started. And this makes a lot of sense when we're talking about distances. When you're talking, you walk 4 meters and then you walk 3 meters. But it works with forces, electric fields. Every vector can be dealt with using this method right here. So don't get distraught when we try and do the exact same thing with forces or electric fields or any even acceleration, anything else that is a vector. So we're trying to find this value right here is our resultant, our total vector. So we remember now we've got a right triangle. And now that we've got a right triangle, we can say that a squared, a vector, plus b vector squared has to equal our c vector squared. So we go 4 squared plus 3 squared equals c squared. So square root of what, 25 equals c squared. So the magnitude of our c vector is 5 meters. Now, what are we missing here for this to be a complete vector? There's no direction on this. Now we can look at our diagram and say, well, it's up and to the right. But that's not very specific. You can't say, well, we need the rocket to go up and to the right. We need very specific values when dealing with physics. So in order to get a specific value, we will try and get this angle right here. So we can get an angle above the x-axis. How do we go about getting that angle? Well, we can go back to our trig functions, and tangent of that theta has to equal opposite over adjacent, which has to equal 3 over 4. And so if we want to get the actual theta value, we do the arctan, or the tan inverse of 3 over 4. And that's approximately equal to 37 degrees. By combining these two factors right here, we have our answer. Our total resultant vector is 5 meters directed at about 37 degrees above the positive x-axis. That is our complete answer. So to summarize our two rules, the first thing you will do, or attempt to do, is deal with the ones that are in line, or they're in the same axis. And with those, you just add. So we'll have, for example, A vector, B vector, and that would be done with A vector plus B vector, whatever those values are, and that will give us our resultant C vector. And if they happen to be pointing in opposite directions, we'd have A vector, B vector. We'd have A minus B vector equals C vector. Or if you like to write it out more specifically, it's A plus minus B vector equals C vector. That is situation number one. Always try and do that first. If you're dealing with them in a right angle to each other, so situation number two is when they're at right angles, you just do the Pythagorean theorem and then you have to do the tangent to get the direction. This will give you the size, and this will give you the direction. And write out a brief example here. B vector, A vector. And we have some resultant vector going off like this, our C vector, at some angle theta from the x-axis. Well, to get the C, it's going to equal square root of our A vector squared plus our B vector squared. That gives us our size, or our magnitude. And to get that angle, so we can give it a direction, we take the arctan, or the tan inverse in this situation, of our B vector over our A vector. So you always do this in this order. You do the ones that are in the same axis, combine those, and then go ahead and take care of any that are at right angles to each other. Using these two rules, you can solve most any vector problem.